Hi everyone, welcome to the structure section of this year's final design review. Like Alan said, I'm Sophia, I'm this year's structures lead. I'll give it to everyone else to introduce themselves.
I'm Jake, I'm a fifth-year Mechie.
I'm Yevgeny, I'm a fifth-year Mechie.
I'm Kyle, I'm a third-year Mecha, and I'm this year's analysis lead.
And then Aries on Zoom.
Hi, I'm Aries. I'm a third-year mechanical engineer.
All right, so like Alan said, this is the basic order we're going to go in for the structures section. It's again the same. There's a little bit more detail on here, and then note the podium session section right after analysis. So starting off with some of our requirements. Structures ourselves has made a couple goals and put some requirements on ourselves, one of them being that 10,000 foot apogee that Alan had mentioned. In addition, we're trying to perform as much FEA on components in the rocket as we possibly can, with a goal of the factor of safety being over 3. We want a thrust to weight ratio greater than 10, and we want to manufacture as many components SRAD as possible, so that's including the machined metal components in the inside, as well as the composite airframe. And then, like Alan said, an efficient motor securing mechanism, which we'll touch on in design. Some of the competition requirements include having a thrust to weight ratio greater than 5, which again, our goal is over 10, so we're not super concerned about that. An off-the-rod velocity of 100 feet per second. And at our separation points, the couplers need to extend 6 inches into either side of that separation point. We also need a factor of safety for our fin flutter, over 1.5, as well as a stability over 1.5 and lower than 4. As far as how we interface with the other sub-teams, which we'll go into more detail at the end of the design slides, but just a quick overview, avionics needs 18 inches of length in a coupler inner diameter, and they need 12 arming and ventilation holes, as well as a camera mounting hole. They also need radio transparency. Payload also needs radio transparency, and payload needs 14 inches of length in a body tube inner diameter. And they need 5 arming and ventilation holes. Recovery needs 16 inches of length for main recovery hardware and 12 inches of length for drogue recovery hardware. And then another thing we have to keep in mind with this competition is our budget. As you can see, we're under 4,000, but the highest cost we have is the motor components, as you would expect, as well as winding and aluminum stock. Starting off with the forwardmost end of the rocket, we'll start off with a nose cone. It's a similar manufacturing process that we've used in the past. It's a 3D printed clamshell mold with a fiberglass layup. And the only difference between this year and past years is that extra straight section that you can see at the bottom. Really the goal of that, or the reasoning behind that, is just for easier integration with the 12-inch coupler that'll sit there. Instead of trying to manufacture a nice point at the top using the layup and mold, which has proved to be difficult, we're going to manufacture an aluminum nose cone tip. That's going to be held in by both epoxy and that threaded rod that you can see goes down the entire length of the nose cone. There's also a nose cone bulkhead in there, which is responsible for most of our stability weight that we've added. In analysis, we'll go over that stability weight, or highlight that stability weight a little bit more. But that's one of the only bulkheads that's not weight reduced. And then ending off in the nose cone, we have the clover bulkhead and the U-bolt that has the drogue recovery attachment. All right, I'll send it to Aries.
As Sophie mentioned, the last part of the nose cone assembly is comprised of the clover bulkhead and the ring, which mate together as shown. 4 M4 bolts will be used to secure it together, and we will be using blue Loctite to ensure that they stay mated. The removable bulkhead allows for the beacon and weights to be accessed in the nose cone and provide a mounting point for recovery hardware. This is also a new design to IREC.
Continuing work we've done in previous years with our body tubes, we're going to be using our X-Winder filament winding machine to make all of our body tubes. The main difference is that this year they're all going to be fiberglass. In previous years we've used a combination of fiberglass and carbon fiber, but this year we're going with a single material so that all of our outer diameters can be consistent, and also because both our avionics and our payload require radio transparency, so that just makes it nice and easy. We're going with 3 layers of 60 degrees because we found that to be a good combination. And this year we are also implementing some new steps that improve our surface finish, mostly during the post-processing phase. So for example, we have these little 3D printed fixtures you can see down there that allow us to put our tubes that have been taken off the X-winder back on so that we can spin it while we're standing. We have a variety of different bulkhead designs in the rocket that differ depending on their location and their function. So we're going to start with the booster bulkhead. This sits right above the motor tube, right above the motor in the motor tube, and it gets epoxied to the outer surface of that tube. The job of this is just to transfer the snatch force to the booster section. We've gone with a 3-spar design to maximize the area between the spars. So in this case, we're going to be mounting one of our recovery beacons between the spars. And I should say this is made from 6061 aluminum. Moving on, we have our top avionics bulkhead, as the name would suggest, that sits above the avionics section, but it's not epoxied in place. Instead, we have 2 holes that go in threaded rods that run through the length of the avionics bay. And as you can see, it's not weight reduced, and we actually need that mass to help with the cooling of our VTX, which we'll talk about later on in the presentation. There's a variety of mounting holes for parts on the avionics section. Our bottom avionics bulkhead is similar. It also has the holes for the threaded rods, but it is weight reduced. This gets epoxied into the coupler tube in the avionics section and gets fixed in place. Moving on to the fins, I'll pass it back to Aries.
Thank you. So moving on to the fin can, we will have 4 trapezoidal fins of 3/16 inch thickness. It will be made of carbon fiber from Dragonplate, one of our sponsors. The dimensions were optimized using a custom MATLAB script, which will be spoken about later, and the dimensions will be optimized again after more components are manufactured, as Alan mentioned. The fin tabs are cut in a way that mate with the fin support structure will be talked about next. So the fin tabs will slot into the rings of the support structure, and the support structure is held up by the interlocking bars. These are to provide surface area so we can epoxy the fin tabs to the structure. The structure forms supports like an internal jig, which makes it easy to set the fins 90 degrees apart. It will be made of 1/4 inch carbon fiber and will also be from our sponsor Dragonplate. The top of the fin support structure bars slot into the boat tail, and the boat tail would be printed out of PETG and has a lip on the end to mate with the thrust plate. The taper length was increased from previous designs to accommodate from a longer motor.
So ending off those specific design slides with our motor securing mechanism, our thrust plate and motor retainer have a similar function that they have in the past. The only difference is that instead of bolting on, this year the motor retainer is screwing on, as shown in the diagram, and it's going to be retained with 2 screws in the sides. We're also planning on manufacturing a gauge to use to make sure that those holes are lined up. The main reasoning behind this change in design was so that we could improve our efficiency in in-field integration, as was outlined in some of our requirements. So more in detail on those interfaces that we talked about in the requirements. Avionics needs 5 arming holes in the vertical sled section, as pointed out in the diagram, and they need 7 ventilation holes throughout the live video section. 4 of those are specifically dedicated to their heat management solution that they'll go more in depth in their section. And then as far as the keying geometry goes, it's pretty straightforward. It's again those 2 threaded rods that Jake had mentioned, and the bottom bulkhead is epoxied in place to stop it from moving and to make sure that all those arming holes are lined up. In addition, they have wire pass-through holes in each of those 2 avionics bulkheads. Payload is pretty simple. There's 5 arming and ventilation holes, and then they have a pinhole. So the pinhole is positioned directly across from the rail, and then 2 arming holes are stacked directly above it, and then there's 2 ventilation holes 90 degrees on either side. They don't require keying geometry, but as you can see in the diagram, we have extended the coupler 3.5 inches up from the avionics section so that the payload Sabo sits on the lip of the coupler rather than directly on the eyebolt and recovery hardware. So as Alan mentioned, we do have a dual bay recovery system. So our drogue separation point is between the nose cone and that upper body tube, where the payload sits, and then our main recovery separation is between the lower body tube and the booster body tube, between like where the payload sits in the booster tube. And both of those are held together with four 440 nylon shear pins each. In addition to our in-flight separation points, we have a additional separation point for ease of access for avionics. So this separation point is between that upper and lower body tube that I had mentioned, between where the payload sits and the avionics bay sits, so that avionics is able to integrate the bay and properly arm it. And this is held together with 3 M5 screws. All right, I'll send it to you to start analysis.
Thank you. So one of the step changes in our analysis this year is the ability to programmatically simulate the rocket. Essentially, because OpenRocket is distributed as a Java program, it comes with a class file and a Java runtime. And if we point MATLAB at those, we can then invoke virtually all of OpenRocket's functions from within MATLAB. Specifically for us, that supports numerical optimization of vehicle components. So that would be, so we'll get into that when we talk about optimizing the fins. That can be either using a simplex search or by using an exhaustive search. We can also do Monte Carlo analysis. We'll also get into that a little bit more, where we randomly vary parts of the rocket and the environment over thousands of simulations to get a good spread for our key metrics. We can also get automated summary data. So the weights and measures appendix is a good example, and a bunch of other parts of the technical report that are very straightforward to do, and they can just be automatically produced from the OpenRocket without any manual intervention. Finally, this is more relevant for future projects, but I figured it would be worth mentioning. We can invoke OpenRocket's Berryman calculator. So if we want to run a dynamics routine in a software other than OpenRocket, for example, Simulink, if we want to make more modifications to it, we are able to get the aerodynamic calculations and use them elsewhere.
Flight risks for this year include the COTS railguide catching on the rails. Previous IREC teams have noticed that the rails at Spaceport America have been rough, corroded, or even sharp. We're going to mitigate this problem by cleaning the railguides beforehand and using a proven COTS solution. The risk of the body tubes failing under boost is moderate. The body tubes are constructed in a similar way as they were to last year, but we do have a higher thrust motor than we did last year. We're going to mitigate this by conducting physical testing on the tubes to ensure they have a minimum factor of safety of 3. Similar to the body tube, the boat tail can also fail under boost. We are going to mitigate this probability by conducting physical testing to ensure the boat tail also meets a minimum factor of safety of 3 as well. The fin flutter leading to fin failure is a low probability, but we have seen this on other high-powered rockets. We are going to design the fins to a minimum factor of safety of 1.5 using the fin flutter equation, which will be detailed in further slides. This is a display of the center of gravity and center of pressure throughout flight. The center of gravity will naturally shift forward towards the nose as the propellant burns. The center of pressure will change with the rocket's velocity. During burnout, we will have the maximum velocity of the rocket, and the fins will experience their maximum pressure. This is when they become the most effective, and the center of pressure will be closest to the fins. As the velocity falls back off, the center of pressure will naturally shift forward back towards the nose.
As mentioned previously, fins were optimized using a custom MATLAB script that interfaces with OpenRocket. It used an exhaustive search where the solution set is discrete, taking geometries from OpenRocket and varying it from 80 to 120%. The geometries varied are shown here. This method was used to avoid local extremum and to ensure that we were testing all possible combinations. To accomplish this, a grid was created with all possible combinations assigned to an iteration number. Each iteration tested a different set of geometries. 98,000 simulations were tested. There is a final overarching check for geometry that is bounded by fin flutter factor of safety, apogee, off-the-rod stability, and stability at burnout. Planned work includes considering parallelization and course optimization to reduce the number of sims. Currently, there are graphs that are available for this if anyone needs to see them. Our fin flutter calculation is governed by this equation from apogee components. Our variables and intermediate calculations are shown here, and it resulted in a factor of safety of 1.58, which is greater than our requirement of 1.5.
As Aries mentioned, we are using the fin flutter equation to design our fins for a factor of safety of 1.5. This equation assumes that the fins are made of an isotropic fin material. They are not. They are anisotropic. This will lead to an overestimation of the fin flutter velocity, potentially leading to an overly optimistic factor of safety. We've selected the M6000 ST motor because it delivers 9,606 Newton-seconds of impulse in just 1.6 seconds. This will get us off the rod faster than 35 meters per second, which is very quick, and get us into a stable flight profile extremely quickly as well. This also brings our thrust-to-weight ratio above 20 to 1. This is a plot of our stability versus angle of attack. This was done at Midland, Texas, using an 84-degree launch rail. You can see that we reach 1.52 cal off the rod, and we don't go above 3.67. As Yev mentioned earlier, we can now do Monte Carlo simulation on the rocket. We did 2,000 simulations varying the wind direction, wind speed, and temperature. And I will specifically highlight the stability off the rod, or the sensitivity of the stability off the rod due to wind, and the typical values for apogee height and stability off the rod as well. On the top graph, you can see a histogram of our stability off the rod from the Monte Carlo simulations. Like I said earlier, the average stability was 1.51, but you can see that there were simulations that did have stability off the rod lower than 1.5, and I will address why this is not a problem in the next slide. On the bottom histogram, you can see the apogee, the histogram of the apogees. The average apogee was about 10,151 feet, putting us comfortably in between the plus minus 10% bounds that Alan set for the team. On the left graph, you can see the stability off the rod versus the wind speed. We simulated wind speeds from 4 meters per second all the way past 10 to see how OTIS would perform in varying wind conditions. You can see on the right graph that at about 15 miles per hour or 9 meters per second, the average time to 1.5 cal was about 55 milliseconds. This is how we confidently set our go, no-go wind speed to 20 miles per hour. This is the load case for the rail guides. We calculated that the upper rail guide would have about 50 pound force and the lower rail guide would have about 20. We calculated the snatch force during main deployment to be about 807 pound force. This was done using Midland, Texas conditions for what it would typically be during IREC using the drag equation. We are targeting a 24 meters per second drogue velocity. The snatch force calculation assumes a couple things. It assumes that the parachute opens instantaneously, which is not true. This is going to lead to an overestimation of the snatch force, potentially giving the bulkheads a higher factor of safety than necessary. It also assumes that the manufacturer specifications for the drag area and drag coefficient are correct. Previous teams have noticed that the manufacturer specifications are usually underreported, giving us a snatch force value that is higher than calculated.
So with those snatch force calculations that Kyle just described, we did a breakdown on how they affect the different recovery bulkheads throughout our rocket. So we did 2 load cases for snatch force, one for the drogue snatch force and one for the main snatch force. And the big thing on this slide is to note that the bulkhead labeled C, right under the avionics bay, it undergoes the highest force at 432.4 pound force. We also did another load case for boost because, as was mentioned earlier, our motor has a shorter burn time, so we're a little bit concerned about the compression at boost. So on the fiberglass body tubes, the highest load at boost is 1,267 pound force, and so that's what we'll use when we compression test. And then the highest compression force throughout the rocket is, as you would expect, on the boat tail, and that is 15,000 pound force. And then I'll give it to Jake.
So although we've used a similar setup with a 3D printed boat tail inside of a cardboard motor tube around our motor casing in the past without any failures, we still want to do some analysis to make sure that the heating of the motor casing doesn't have any negative effect on the strength of our boat tail. And so we set up a transient thermal analysis in ANSYS. The settings are pretty simple. We're assuming that the inside surface of the cardboard motor tube, which is insulating, is at the limit of 200 Celsius, which is set in place on all motor casings. And then we are running it for about 1.6 seconds, which is the length of our boost. After that, we're not as concerned with the strength of the PETG. And as you can see, during that 1.6 second simulation, we have a nominal increase in temperature from about 38 Celsius to 42.3 on the inner surface of that PETG boat tail, which is much lower than the glass transition temperature of about 85 Celsius. So not a concern. We've also run simulations on all of our different bulkheads with the snatch force that we expect them to see. So starting with the clover bulkhead, this sits in the nose cone. In this case, the clover ring is epoxied to the inner surface of the coupler, and then our snatch force is applied through a U-bolt to those two holes on the spars of the bulkhead. As you can see, our safety factor is quite high throughout the bulkhead. Again, we're shooting to be above 3 on all of these components. For the lower avionics bulkhead, there's 2 load cases. In the first load case, it's fixed with epoxy around the outer surface, and then we're applying that snatch force through the eye bolt in the center. We have a safety factor of much above 3 throughout. The second load case involves the snatch force coming through those threaded rods instead of the eye bolt, so you can see that reflected there. And again, our safety factor is much higher than 3 throughout. You can see there are some stress concentrations around those holes. For the upper avionics bulkhead, this one's not weight reduced. It's also not fixed in place, and so the retaining is actually done on the mating surfaces of those nuts, which go on the threaded rods, and then our snatch force is applied through the eye bolt in the center. And again, as you'd expect, we have a very high safety factor throughout this component. And then finally, the booster bulkhead. This is epoxied around the outer lip once again, and then our snatch force is applied to the eye bolt. And although this is a 3-spar design, we do have some stress concentrations around the outside of those fillets. Again, we're much higher than 3 throughout the bulkhead. For our thrust plate, we're applying our thrust from the motor casing on a small contact lip that sits on the inner surface of the thrust plate, and then we're epoxying it to the boat tail on that top surface. And finally, we end up with a safety factor above 3 throughout, with a stress concentration where the casing makes contact with the thrust plate. And then just a quick summary of all of our safety factors. In the event that we have multiple load cases, we've put the lower of the 2 safety factors here, but as you can see, they're all above 3, so no concern.
So as was mentioned back in requirements, our thrust to weight ratio is something that we put a lot of effort into, and with that we tried our best to weight reduce as many components in the rocket as we could in combination with that FEA that we performed. So we kind of used this as a guide throughout that, so you can see that our bulkheads have a really low percentage of that total mass because we did do as much as we could to weight reduce them when we had the opportunity to. So finishing up the structure section, we'll look at some of our goals going forward and how the time between now and the competition is going to go. So like I mentioned earlier, we're trying to manufacture as many SRAD components as possible, and with that goal, we have quite a big manufacturing plan. So up here is listed the components that will actually be in the rocket, so the metal machine components like the bulkheads, the nose cone tip, the thrust plate and motor retainer, but it also includes like a custom fixture plate for the bulkheads, which is at the top. It also includes our test fixtures in here, as well as all of our composite work. As I mentioned, we also plan to perform 4 tests. So we're compression testing the fiberglass body tube as well as the boat tail. We've done variations on that in the past, but this year we plan to really improve those test processes. And we also plan to test the epoxy joint of bulkheads, which we've done in the past, and then the strength of the rail guides as kind of outlined in Kyle's load case in the analysis section. So with a manufacturing plan this large, there's always risks that come up. the tubes, any composite work may not be finished in time. We're not really concerned about this issue. We only have one more tube to wind. But if something happens and for some reason we don't get it done, that could be a pretty high severity. It could force us to change to COTS tubes, which would be unfortunate because it would essentially have us fail our SROD requirement that we placed on ourselves. But again, like I said, unlikely. The tubes could produce an unacceptable surface finish, which, depending on severity, could put us back 2 weeks just to rewind, or it could force us to switch to COTS. The boat tail or the tubes could fail compression testing. With the boat tail, that would likely just cause a redesign and a reprint, which could put us back 2 to 3 weeks, depending on when we have access to the 3D printer. The tubes, that would probably force us to switch to COTS. Again, not super concerning given our analyses, but there's always the risk. And then just general, the unfortunate reality, that machines and tools are down and shipping delays, but we did make this manufacturing plan. We have a good timeline set out so that if any of these things do come up, we will still have enough time to overcome them.